Hello guys, welcome to OLED Wave channel again. We're a channel that's focusing on reading the latest archived works on speech and NLP. Today, we're going to be reading a paper which was published last year. Its name is SpeechT5, Unified-Modal Encoder-Decoder Pre-training for Spoken Language Processing by researchers from Southern Universities of Science and Technology, Hong Kong Polytechnic University, Hongji University, Microsoft, and the Panchain Laboratory. Before I start, I think most of you might already heard of Google's T5. So what does it do? The paper also gave you a tutorial on this, but I try to use a one sentence to explain it. So think about in this NLP, there are many NLP tasks. For example, entity recognition, QA, whatever. And you can get a common features of those tasks, which is you always have a input textual sequence and a output textual sequence. So basically what T5 would be doing is just regardless what the task is, they just train one unified T5 encoder and a T5 decoder model. This is the input, and this is the output. So whatever the task is, just flows in and flows out. So they share the encoder. I think most of the time they will share the encoder, but they also share maybe a part of the decoder. And of course, in the end, they will have a separate or different decoders for each task. Then they could be able to accomplish different tasks. And also they may also have different encoders for different tasks. And the benefit of the T5 is that for different tasks, they would be able to share the encoder and decoder in terms of the parameter. And that helps, in my understanding, helps the cases. For example, some task, it does not have enough amount of training data, but can benefit from this. And today, or last year, those researchers, they borrowed the ideas of T5 and try to apply this to the speech domain. And the most important sentence you want to read is this. They want to, this one. Sorry. The purpose of their T5 is to get a framework for learning joint contextual representation for speech and the text data via a shared encoder-decoder structure. So you can see, again, it's the same as T5. They share the encoder and decoder structure, but this time the difference is that the input is no longer only text, but they have the speech as input. And sometimes they would also have speech as output, because for speech-related tasks, you can have ASR task, which take the speech as input, but you can also have a textual speech task, a speech synthesis task, in which the text is used as input and the speech would be as output. So it's slightly more sophisticated than T5. And you may ask, why did the researchers want to do this? Let's go to the introduction. They address that the speech pre-training work mostly suffer from the two problems. I would call two issues, because to me, it doesn't look like it's a problem. It's more like an issue. And I'm also skeptical about the wording here, suffer. I mean, they are facing more than maybe not suffering, okay? The first thing is, when they trained the self-supervised training. For example, Wave2Vec, Hubert, or WaveLM, they learn speech representations from a bunch of unlabeled data. But remember this, those data are speech data. They also have high-level information in it, which is text, or what the people actually say. And for those information, they were completely ignored during the training of those speech pre-trained models. But some people may argue that you don't have the transcription, or if you're using the speech recognition results as the text as input, then you are facing the chicken egg chicken problem, or you're not doing the pre-training, you're doing the semi-supervised learning. Okay, but different people have different opinion. The second issue, I think, as the author mentioned, is that how you design a framework that can take advantage of the unlabeled speech and text data. I think it's related to the same the first one. Okay. And this all comes with this modality transformation. I learned the new word today, a modality transformation. It means, suppose you're doing ASR, you're going from speech to text. Suppose you're doing TTS, you're going from text to speech. You're doing speech enhancement, there's no modality transformation because it's speech to speech. But most time it involves speech, right? Okay. I think the second one, they actually also talk about, most time people just using the speech encoder. They do not use the textual encoder in there. Okay, that's true. Okay, let's move on to the model. I think the model is fairly easy to understand. But don't be scared by those so many boxes and lines and arrows. What actually they were talking about is the building framework. You can see the encoder and decoder. For those of you who have already subscribed to our channel, you can go back and check transformer video. Transformer. Attention is all you need. So this encoder-decoder structure is exactly the transformer architecture. Or in speech, people call that attention encoder-decoder structure, AED. Same thing. And the first time I saw this, I got surprised that they are actually concatenate the embeddings from the speech encoder and the text encoder. Actually, they are not. This is OR. They should have a switch there to make it more clear. And this is also OR. You can just have one encoder input only at one time. For example, you're doing the speech recognition task. Let me use another color of pen. Suppose you're doing ASR, okay? Then you are passing this through a speech encoder. This actually, they use a pre-trained model or SSL model. For example, Wave2Vec 2.0 or Hubert. Search those keywords in my channel if those words are new to you. And you can also subscribe our channel if you like our channel, because I'm the few channel that has all these speech models, especially those pre-trained models, explained in a systematic way. And after this, you pass this through encoder and then decoder. So for ASR, so you're gonna be using this one because it's the because the transformer it is most time is a autoregressive model. So actually, definitely you're gonna have this one, right? At the final decoder, and then you're gonna get the output of Y, but the Y would be fed back into the decoder's input because this is autoregressive, right? And then you ask, what is text encoder, a decoder. I think according to their paper, they're saying this is it's trivial. I think it's trivial. What they actually talk about is this is a text decoder trained on Libre speech external text data. So for Libre speech, it's 960 hours of training data with transcription, but the text decoder or text postnet text decoder are not trained on those data. They're trained on another data set, which is also provided by Libre speech dataset people. Those are just text related to the Libre speech task. You can see those texts are in the same domain. There's also some book text data, but there's no audio. Okay, they just use the text to train those networks. Make sense? Then let's see. Suppose we want to train a TTS model. What the module they should be using. So for the TTS, speech is no longer as your input. So you're gonna be using this one. Of course, you're gonna be using the shared encoder, also the shared decoder, and also because suppose your TTS is all regressive, then you're gonna be using the speech decoder this time as your prenet here. Okay, according to their description, this is just a 3 fully connected layers. And what is this? This is a log mail feedback. Just Google this word. I'm not gonna spend time explaining this to you. And the output is something like the log mail feedback 2, right? So they're gonna be using this one, not this one at all, but they're gonna be using the speech text encoder. This is shared one, and this is it's autoaggressive. All right. So I explained the TTS and the ASR scenario to you, but if you're interested, you can do the homework by yourself. So say, what is the speaker verification scenario, and also say speech enhancement scenario. You can do it yourself. It's fairly simple. But up to now, we haven't come up to the most important part, the key part of their model, because you think, is that easy to train a model like this? But they have not mentioned the most important part, is the training, the details of training this speech and text encoder, which is also shown magnified over here. Well, the point is, as they mentioned that in the joint pre-training subsection, they're saying that you can imagine this. Suppose you're doing this training, what you can see. So because every time you try to train with the ASR or TTS task, there's only speech or text being presented to the encoder. They're not presented there at the same time. So the question is, how do you align the space of the speech representation with the space of the textual embedding? And only by doing this, you can say that I found a way to incorporate, what do you say that? I think I want to use the author's original words. They defined a way of training a joint contextual representation for speech and text data. So say at the speech text encoder output, it's an embedding, right? So the embedding can not only be viewed as a speech embedding, but also as an embedding of that text. So this is new, and this is what the authors was trying to do. And they're mentioning this in the joint pre-training. So they propose a cross-modal vector quantization method to learn the representation capturing the modal invariant information. So here is what they do. First, let's look at the equation number 4. What does this mean? So U sub I means the speech or text representation, and Cj means the center or the discrete representation of a fixed size code book. So once you get a representation, either speech or text, this equation 4 tells you that the author wants to find, the equation 4 here. The equation 4 tells you that the authors want to find the exact code in that code book which is closest to your representation, or doing the nearest neighbor search, okay? And that they're using the L2 distance. That's simple. I mean, do you agree with me? But by doing this, then you can imagine this. After you're doing this, so every representation U sub I at each frame or each chunk or segment, each time point, I would say each time, okay, they can be mapped to or quantized to a embedding, and that embedding, both speech and the text are sharing the same feature space, share the same code book. And you can imagine this. They're drawing a illustrative figure here. Suppose the speech code book is located here, not located, okay, latent representations, okay, and then the text is located here, okay. They're trying to make these two spaces merge together, something like this. There's more details here. Actually, they are not replacing all the continuous representation into the discretized code book codes. You can see after quantization, they also choose to keep some of the continuous representation to be in the next or passing through to the next layer. They kept some of them. And you see, for example, 1, 2, 3, 4, 5, the first and the fourth continuous representation got kept to the next stage, but only number 2 and number 3 got converted to the discretized codes. So the benefit of doing this, according to the author, is that they can explicitly guide the quantizer to utilize the cross-modal information, and because they can calculate the cross-attention upon the mixed representation. The mix means it has a discretized and the continuous ones. Okay. Then I finish explaining this. Let's jump to the experiments. They have done experiments on ASR, TTS, speaker ID, voice conversion, speech translation. What else? I might miss something. Oh, speech enhancement. So you can imagine this is similar to T5, Google's original T5. Have lots of different tasks, but they're all using share the same encoder-decoder. But this one is red pen here. Yeah, can I go back to the red pen? Anyway, I'm getting this pen. Don't forget this. This is 100 hours, but the result is very impressive. So this is with LM. This is without LM. They're both doing better than the other ones. But I'm personally more interested in the full size of the LibreSpeech dataset. You can see this, I think, in appendix number C. Okay, it's here. This is no LM. This is the with LM. And the result, I would say, is very impressive. I think this is, how to say that? It's almost a state of art. Or is it state of art? I'm not very sure, but definitely sorta. Because I remember that recently people from Assembly or some, yeah, or ASAP, not Assembly, ASAP company, they release something like the 1.75 in terms of error rate, but they do use a pre-trained model which leverage the external audio data. Okay. And the external audio data contains about 60,000 hours of LibreSpeech-like audio. It's called LibreLite. But for this one, it does not use any external audio data, and it only uses the textual data given by the LibreSpeech. Of course, they use the external text data database without audio transcription, and they leverage that to train their text encoder. I will cover that later on. But they didn't use extra LibreSpeech data. So this is a fair comparison between these ones. So pause the video if you ask yourself this question: is it really fair? Okay, the answer is that it's not exactly fair. Because why? Let's see this. Okay, let's check the model again. Okay, it's the training of the text encoder make the comparison of their method with other method unfair. Because in most of the other algorithms they compared with, the LibreSpeech external text is only used to train a RNN language model or transformer language model, which is later being used for rescoring. You know what is rescoring? You get a first pass decoding result, for example, embeds or a lattice, then or graph. Then you use the language model to get a new scores on the paths or arcs on the graph. So the graph, when you want to search the shortest distance in the graph or the minimum cost path in the graph. So in that way, the path calculation would be, again, different compared to your first pass because the language model changed the scores on the different arcs. Or say, in a simple word, is it adjusts the decoding results based on some expert knowledge, which is not related to your audio database. It's more related to the textual information. So I hope I explained this to you clearly. Then you understand. Then you can definitely understand why it's not fair. Because this, you're not supposed to use this language model together with audio, I think, because it's hard. How to say that? I wouldn't say it's fair. It's not the same. I would use this word. It's not the same compared. It's not apple to apple comparison because Other methods do not use these textual information to train the model which used for the first pass decoding. That makes sense. But the authors may argue that, okay, the other guys, they never thought about leveraging the textual data in the first pass training or together with training with the speech. I think lots of people have tried before. For example, you can check some paper called the Deep Fusion, which is also about getting the some text encoder together with the speech encoder. But I would say in that paper, I don't remember that they use this external text to train their model. They only use the external text in their RN training. Of course, you can do lots of fancy things in your RN training, for sure. But I think to facilitate fair comparison with other algorithm, you should not use this external text. But I think the fair thing would be only use Libre speech. Yes, you got me. Training text. Training audio's transcription, okay? You get me, right? That would be fair. But that issue, I would rather want to see those results if the authors can provide this later on. But I highly suspect that would work or not, because there's probably not enough amount of data to train this pre-net well. Okay. All right. What else? The miscellaneous part things. Well, anyway, I think to conclude, in terms of the results, I would say I'm very impressed by the results on the ASR. They have achieved a lower than 2% of error rate in terms of WER on Libre speech, although they are facilitating something that I do not think that's fair. But they actually didn't use external text database or audio database, which is very impressive. Finally, I want to quickly go over the ablation study. I think this is interesting. To me, that this is a little bit confusing to me because I haven't read the paper in great details. To me, if there's no speech pre-training, how do you train the model jointly, right? But to me, I would rather just look at this one because I think this one is the most important. I think it definitely makes sense to have a speech pre-training or text pre-training, right? Oh, this is interesting. If they do not do the text pre-training, okay, that means they do not have the Libre speech external text database to train their text encoder. The result would be a lot worse. You see, the clean is 4.4, it became 5.4. Let's quickly take a look at. Okay, this got intriguing. I think you can definitely find 4.4 somewhere. Yes, 4.4. But they end up with 5.4, right? It's still better than the base. Oh, it's worse than the baseline. You see, that became the issue. Okay. So yeah, that means if they do not leverage the external text data to train their text encoder, that means they get worse results than their baseline. Make sense? About the joint pre-training, and you can see that ASR only dropped a little bit. So this is only dropped a little bit. So it seems to me that joint pre-training is not that effective compared to the text pre-training. You get what I'm saying? So So the question is the joint pre-training really working, or it's just the text encoder that helps? Asking that question, I would rather ask the next question or the second question. I think most of you, if you have subscribed to my channel and watched lots of video of mine, you probably ask the question by yourself. Pause the video to see whether you can ask the question about the ASR. Right. They only compare on the Libre speech task. They have not compared on the other task. Whether the algorithm can be generalized has not been tested. So let's say besides Libre speech, you also have a switchboard task, or switchboard task is telephonic speech recognition, or TED Talk. I mean, for the T5, all the QA tasks, they can have multiple QA tasks, right? Multiple speech entity, name entity recognition tasks. But those datasets are sent into the same training framework, which means that eventually they're going to be ending up with just one single model, which is targeting different tasks and the same task but different data sets. Okay. So the question I have is that suppose you just have the Libre speech and the switchboard and the TED Talk and different speech recognition tasks, and you all send your training data through your framework. Would this thing still be working? Because in this way, in this time, I think your speech would be scenarios will be mixed together, and your text, what to say that? The topics of your text content would be different, right? And would that still be working? I didn't say it won't work. Okay, I would say just that this is an interesting question to explore. All right, I will stop here. Thank you for watching. If you like our video, please share that with your friend and subscribe our channel. Or finally, I have some time for you to ask me questions. But my online audience, do you have anything for me? I will count to 5. 5, 4, 3, 1. All right. Thanks again for being with us. Finally, we are actually a meetup in the Bay Area. So if you're a company or institute in the Bay Area and want to sponsor us with a meeting or conference room, because that will be, we will super appreciate that, because we were always thinking of to have an offline gathering sometime so people can get to know each other. And I think it's better to have face-to-face discussion of those papers. People like to ask questions, right? This is the most important things, asking questions. All right. Thank you. All the best. Bye.